Today, we're going to take a look at one of the most famous experiments in all of science, but we're doing it with a twist. A twist that could seriously rewrite the rulebook. For about a century now, we've had one main explanation for the biggest puzzle in the quantum world. But what if that explanation isn't the whole story? Well, a new theory has just stepped into the ring, and it's making some incredibly bold claims that we can actually test. So, yeah, let's dive right in.
It all boils down to this one deceptively simple question. Does the universe behave differently when we're not watching it? I know, it sounds more like philosophy, right? But in the quantum realm, this isn't just a thought experiment. It's a very real, measurable puzzle.
And the place where this mystery really comes to life is the famous double-slit experiment. For more than 100 years, this thing has been the absolute cornerstone of quantum mechanics, a puzzle that really just throws the sheer weirdness of reality right in our faces.
Okay, so how do physicists actually explain this? Let's start with the reigning champion, the standard model of quantum mechanics. For decades, this has been the accepted, go-to explanation.
Now, the core idea in the standard explanation, it's a little abstract. It's not about physically bumping into a particle or disturbing it in some clumsy way. No, it's all about information. Specifically, it's about whether or not you have access to what's called witch path information, basically knowing which of the two slits a particle actually went through.
So let's just walk through this. When you're not looking, a single particle, say an electron, acts like a wave. It somehow passes through both slits at the same time and creates this beautiful interference pattern on the screen behind it. Those classic light and dark stripes. But, and here's the kicker, the second you put a detector there to see which slit it went through, that pattern completely vanishes. Gone. The electron suddenly starts behaving like a well-behaved little particle, and the stripes are history.
And that right there is the whole ballgame for the standard view. The act of measuring, of getting that witch path information, it tangles the particle up with the detector. This connection destroys something called phase coherence. A good way to think about it is like two perfectly synchronized swimmers who are just gliding through the water in perfect rhythm. Then suddenly they fall out of step. That orderly relationship is broken, and that's what kills the interference pattern.
But what if there's another way to look at all this? This is where our challenger comes in. A new model called the Harmonic Scale Framework, or HSF for short. It's looking at the exact same experiment, but from a completely different and, you could argue, a more physical perspective.
Okay, so the huge shift in thinking with HSF is this. Particles aren't tiny little points like little billiard balls. Instead, HSF pictures a particle as a stable structure made of a few different waves that are coupled together. Think of it more like a musical chord that's holding a steady, stable note. They call these things standing resonances.
So let's put these two ideas side by side, because this is where you really see the difference. In standard quantum mechanics, you've got this one single wave function that describes all the possibilities, and when you observe it, you collapse it into just one reality. But in HSF, a particle is already made of at least two coupled waves. Observation doesn't collapse anything, it decouples them, it breaks them apart.
And this whole idea of decoupling lets HSF offer up a really physical, almost mechanical reason for what's going on. They have this cool name for it, the lock and leak principle.
To get this, HSF says you have to think about the particle's wave as having a few different parts, or what they call channels. So one part, they label it K1, is what determines where the particle is going to land on the screen. Another part, K2, is the one carrying all that crucial phase information. That's the component that creates the stripy pattern. And then there's K3, which is basically the outside world, the detector or any other interaction from the environment.
Now, when the particle is just flying along, totally undisturbed, its K1 and K2 waves are perfectly synchronized in what HSF calls a harmonic lock. They are perfectly in step, working together like a well-oiled machine. And it's this beautiful synchrony that allows that interference pattern to form in the first place.
But when you bring in a detector, that K3 channel we talked about, it connects with the particle. And this connection creates what they call an energy leak. It's like it siphons away the phase information. This leak breaks that harmonic lock between K1 and K2. They fall out of sync, and just like that, the interference pattern is toast. So what we have here are two very different stories trying to explain the exact same result. But this is where it gets really exciting. HSF isn't just a story. The challenger is making concrete, testable predictions about where it actually disagrees with the champion.
And honestly, that is the key. This isn't just another interpretation for people to debate over. The harmonic scale framework makes physical claims, stuff you can actually go into a laboratory and test to see if it holds up.
So let's look at the tail of the tape. HSF predicts that if you do a partial, sort of gentle measurement, a faint interference pattern can actually stick around. Standard QM says, nope, absolutely not, impossible. HSF also says the pattern disappears at different rates depending on how you measure, whether your detector targets that K1 or K2 channel. QM, on the other hand, predicts the loss of the pattern should be uniform. I mean, these are clear, major differences.
But out of all these predictions, there is one that is a total game changer. HSF claims that even when you have solid witch path information, when you know for a fact which slit the particle went through, a small residual interference pattern of about 5 to 15% could still be visible.
Let's be crystal clear here. According to the standard model of physics, what I just said is impossible. It is, and I'm quoting directly from the source material here, absolutely forbidden. If this prediction is ever confirmed in a lab, it wouldn't just be a small correction. It would force a fundamental rethink of quantum reality itself. It could open doors to new technologies we can't even dream of right now.
So where does that leave us? It's a pretty fascinating spot to be in. We have a reigning champion theory that stood for a century, and now a bold new challenger with a list of specific predictions just waiting to be tested in a lab. Could the next great leap forward in physics be hiding right here in the details of an experiment we thought we already understood? The results of those tests? Well, they could either cement 100 years of physics or launch us into a brand new era. Only time and, of course, the data will tell.